begin the discussion, I will again recall a few things that you learned in your second year level under Thermodynamics 1, so that we can build on that from next week onwards. So I'm sure all of you know that the compression ratio is a dominant parameter in engine performance, which in fact directly related to the thermal efficiency of an engine. So this curve is the compression ratio versus the Otto cycle efficiency, the thermal efficiency of air standard Otto cycle, which is the ideal cycle. So as you can see here, the thermal efficiency of an ideal cycle exponentially increases, as you can see here, with the increase of compression ratio. So if you can recall what you learned in your second year or in the first year, when you look at thermodynamic cycles, the Otto cycle efficiency can be represented using this equation, where K is the property of the fuel, or the, in this case, the air. That is the specific heat ratio. And of course, as you can see here, the thermal efficiency increases with the increase of compression ratio. Now, the compression ratio, what is compression ratio? The compression ratio is basically the ratio between the maximum volume and the minimum volume. The maximum volume is the displaced volume plus the clearance volume. Minimum volume is the clearance volume when the piston is at the top dead center or topmost position in a vertical inline engine, for example. Vertical engine, when the piston is at the topmost position, there is a small gap. That gap is the clearance volume, and when the piston is at the bottom dead center, at the far below position, the maximum volume is the displaced volume, the amount the piston displaced, plus the small space at the top, that is the clearance volume. Now, as you can see here in this curve, now when you increase the ratio, that means if you reduce the clearance volume and increase the displaced volume, if you reduce the clearance volume and increase the displaced volume, then of course you will be able to increase the compression ratio. That is, then you can increase the thermal efficiency. Now in petrol engines, can you go for a very high thermal efficiency by increasing the compression ratio? Now, when you look at this curve, you can go up to 70%, for example. Can you achieve 70% of thermal efficiency by just manipulating the compression ratio? No. Why is that? Before we ignite the gases using the spark plug, the gases can start igniting on its own due to high pressure and temperature created due to increased compression ratio. So that phenomena is called knocking. So there will be an very undesirable phenomena take place, that is called knocking. So that the gases will start igniting on its own, particularly close, the gases close to the walls, filling the walls and the piston crown. We talk more about this when we talk about combustion. So there will be some undesirable practical situations created if you go beyond a certain value when you as far as the compression ratio is concerned. So there is a limit that you can increase the compression ratio. There is a practical limit. Therefore, usually the limit is around 10 nowadays. We can find engines with the compression ratio 11, 11.5, something like that, but you can't go beyond that because of this knocking problem. So, so always the increase of compression ratio is limited by knock. So we talk more about this knocking, how it happens, and the kinetics of knocking and things like that later. So there are limitations as such. Mean piston speed is an important geometric property of or the parameter of an engine, particularly when it comes to design of engines. We know that the piston velocity changes at the top dead center and the bottom dead center, and the velocity becomes zero, the speed becomes zero at both the top dead center and the bottom dead center, and then it gets accelerated. So it's a dynamic quantity, so we can't quantify the value of piston speed.
but mean piston speed, of course, we can give an average value for the piston speed and get an understanding about how fast the piston moves up and down on average basis. So the mean piston speed is computed by multiplying by using this equation 2L into N, where L is the stroke of the engine and N is the crank speed in revolutions a second. So you get this quantity in meters a second. When it comes to design of engines, what we are most interested in is not just the mean piston speed, but the maximum mean piston speed. So this value will be maximum when N is maximum. So the engines usually run at a wide range of speeds. And when the value of N is largest, the mean piston speed also will be large. And on the other hand, there's another way of increasing the mean piston speed, that is by increasing L, the stroke. There's a limit that we can increase the stroke L, and there's a limit that we can increase the value of N, that is the crank speed. So the maximum mean piston speed could be computed or could be established in an engine by having by finding the correct values of L and N. When the engine is operated, there's a lubricant layer between the piston and the piston sleeve or the cylinder. So at very high speeds, there is a high chance of breaking that film of lubricant, so that the engine wear and tear could get increased. Likewise, there are positives and negatives also in the case of increasing the value of L. Therefore, these parameters are interconnected, and there are positive effects as well as negative effects of change in these parameters. Accordingly, we'll have to make a proper optimization when it comes to design of engines. Now, the instantaneous piston speed, of course, the dynamic quantity, we can find it ds over dt. S is this distance. And usually the instantaneous piston speed could be explained as a normalized quantity to mean piston speed, as you see here. Accordingly, we can get rid of the value of N from this equation, and we can represent the ratio between the instantaneous piston speed and the mean piston speed as a function of theta, where theta is the crank angle, crank rotation, and this R is a geometric parameter, which is the ratio between the connecting rod length and the crank A. So this A, twice A is basically L. Twice A is basically L. So this crank will be at the bottom when the piston is at the bottom dead center, and the crank position is at the top when the piston is at the top dead center. So the diameter of this one, or the twice the radius of this circle, is what is meant by L. So that is mean piston speed. This table indicates the maximum mean piston speed values in meters a second for different type of engines, which is, of course, available at Wikipedia. For low-speed diesel engines, the marine engines and stationary engines, like engines we use for power generation, the maximum mean piston speed is around 8.5 meters a second. And medium speed diesel engines like trains and trucks, it can be around 11. And high speed diesel engines like automobile engines, you can go up to 14. And medium speed spark ignition engines, that is about 16. And high speed engines like sport automobile engines, it can go even up to 25. Likewise, there is a limit of the maximum mean piston speed, as you could recall from the previous slide. So this is 2L into N. As I said earlier, there is a limit that we can increase the value of L, and there is a limit that we can increase the value of N. So accordingly, there is a limit for the maximum mean piston speed.
And another design parameter that we look at when we want to carefully look at when it comes to design of engines is the bore to stroke ratio. So bore to stroke ratio, there is a ratio between engine bore, that is the diameter of the piston or the cylinder, and the stroke is, of course, the gap between top dead center, bottom dead center. And the problem is when you have, as I said earlier, when you have a large bore diameter, bore radius or diameter, if the engine bore is large, then we can find that the surface area to volume ratio increases. That means volume to area ratio. More area in a confined volume. Now, if the surface area is large, then of course the heat transfer is directly proportional to the area, so that area where the gases are in contact. So if the area is large, then the heat losses will be large. So surface area to volume ratio is another parameter that we need to look at in engines to maintain the heat losses at a manageable level. And at the same time, if the mean piston speed is low, as I said earlier, it is better in terms of lubricating capabilities of the engine. And the typical values for bore to stroke ratios of engines more or less. Small and to medium size engines is 0.8 to 1.2. The large slow speed engines 0.5. Like that, there are people have done a lot of experiments and found that these values need to be kept in certain ranges. So the design manuals, design codes and manuals give us certain information about these parameters. So when you design an engine, of course, according to certain standard, then you have to maintain these ratios at the desirable limits. And another parameter is connecting rod length to crank radius. That is, this connecting rod length is this one, and the crank radius is A, this one. Now again, there is a limit that you can increase or decrease this ratio. If you increase this ratio, then this length will be increased. So this is like this is subjected to compression as the piston comes down. So it's like a compression beam. So if you increase the length, then the slenderness ratio becomes a dominant parameter. If you design this as a column, for example, and if the length is large and cross section area is small, then there will be buckling failures and things like that. So that is a disadvantage. So you'll have to make it larger. When you want to make the cross section large, the weight increases, and then again there are inertia losses and issues. The weight of the engine increases, and there are problems if you go for a long connecting rod length. But on the other hand, if you increase the connecting rod length, there is advantage in terms of engine losses. Can you guess an advantage of increasing the length of the connecting rod? If the connecting rod of this one is now this is the connecting rod length, and if you use the long connecting rod than this one, in this particular position of the piston, if this angle is alpha, you use a longer connecting rod than this one, this value of alpha will be larger or smaller. It will be reduced. It will be reduced. So what is the advantage of having a small alpha? Now one of the major issues we have with engines is the friction and heat losses. Those are the dominant behaviors or parameters which decide the efficiency of an engine. Always there's a lot of heat generated within an engine, and this heat means energy goes out, go to waste. And at the same time, there are a lot of rubbing components within the engine, so that rubbing components will create friction, and there are a lot of friction losses. So we want to minimize the heat losses, if you want to increase the engine efficiency, you'll have to make it close to adiabatic process. That means you'll have to make it, you'll have to reduce the heat losses as much as possible. So one phenomena that, as I said earlier, one design objective that you need to look at is surface to volume ratio. So when you have a certain volume, then that volume decides how much of power you produce, because density into volume is mass, mass into calorific value of fuel is energy. So now when it comes to heat losses, the objective function that we look at is, when it comes to design, surface area to volume ratio. You want to minimize the surface area to volume ratio. You want to have a larger volume with small area. That would be the ideal. So minimum heat losses. And at the same time, when it comes to friction losses, now the most of the friction comes due to rubbing action between the piston rings and the cylinder wall, and also there will be certain movement of the piston. Piston also turns this way, and there will be some rubbing taking place over here, this part of the piston as well as and the cylinder walls. So now this friction force is the force coming upside or down, or vertically up or down, as the piston moves up and down respectively. That vertical force comes due to the force, horizontal force applied onto the wall. So the horizontal force applied in this way, if it is R, then mu R will create the frictional force. So if you can reduce the horizontal force, then mu R also will be reduced. So now the horizontal force comes, now the force on this connecting rod is along the connecting rod, so that can be resolved horizontally and vertically. So the horizontal component will create a push. So that horizontal component of force can be reduced if this value of alpha can be reduced, because it is sine alpha. So the horizontal force acted on the piston to twist the piston or turn the piston would be reduced if this alpha is reduced. Ideally, if this connecting rod is infinitely long, then there won't be any horizontal force acting on this. But if, of course, practically it is impossible. Therefore, the length of this connecting rod has an influence on the frictional force on the cylinder walls, between the piston and the cylinder walls. So that is a parameter that we need to look at in the optimization process. What is the best value of alpha at a given theta in order to get the minimum friction force? When you try to reduce this one, maybe the surface area to volume ratio would be increased. Therefore, we have to go for a compromise. So we have to take all these things into account and run an optimization algorithm so that we could find the best values, best set of values considering all these scenarios. So these are interconnected. When you minimize one, some other thing can be maximized. So we have to come for a compromise, a kind of a agreeable set of values. So the connecting rod length is something that affects on the friction forces. And again, the design manuals give us certain ranges of values. So we can optimize a particular engine depending upon our operating requirements by starting from these ranges, and we can pick a value between this range, for example. But we'll have to look at this holistically. Effect of each and every parameter on the overall performance need to be looked at as a combined optimization problem in order to find the best set of values. So when you make something better, other things would become worse. So those things can be looked at carefully. And this is the PV diagram, and sometimes we call this is an indicator diagram. Because in all the days, particularly with the steam engines, This diagram is, there was a mechanism connected to that engine so that this diagram can be drawn, okay, particularly with steam engines. So that diagram can be drawn externally with a mechanism fitted inside. So that mechanism and that way of drawing this diagram externally is called the indicator. Therefore, this diagram is called the indicator diagram. So since this one was called indicator diagram, now we all know that the area under pressure volume curve is work. So the work calculated by using this pressure volume diagram is usually called indicated work. Indicated work. That is, indicated work is more or less the amount of work that engine gives us thermodynamically within the engine. So that is the thermodynamic work that you can get out of this engine is the indicated work. But again, there are a lot of rubbing component within the engine. Therefore, there are a lot of friction losses. Those losses need to be deducted from this indicated work to find out the actual work that you can get out of this engine. So the indicated work is more or less the thermodynamic work that you could expect, practical thermodynamic work that you could expect. That is the conversion of chemical energy to mechanical energy is more or less the indicated work. So the indicated work, we have two types of indicated work. Gross indicated work. So the gross indicated work is, this is the power cycle. So you compress the gases and you expand the gases. So the area under this curve and the x-axis or the volume axis gives us the amount of work required to compress this gas. So I'm talking about this area under this curve and the x-axis or the volume axis gives us the amount of work required to compress these gases. And area of this area under this curve, expansion curve, and the volume axis will give us this area of this and this, give us the work that is produced by the engine through a combustion process. So, and the difference between the area under this curve and this curve respectively with reference to the volume axis gives us this area A plus C. That is of course the gross indicated area work that you can take out from an engine. So area under this curve and this curve. So if you subtract the area under this expansion curve from the area under compression curve with respect to the volume axis, then the area what you get is A plus C. So that A plus C area is called the gross indicated work. And similarly, what you get is down here is again area under exhaust curve is amount of work that you need to do to push air out of the cylinder, and air area under intake curve and volume axis gives us the amount of work that is required to push air in. Now the difference between these two is called the pumping work. That is again this point to this point, that is area is B plus C. So the difference between these, now pumping you have to do some work, and indicated work the engine gives us some work. Therefore we can calculate the gross indicated or net indicated work by subtracting the two quantities, whatever the engine produced and whatever we want to use to pump air in. So that means the net indicated work is the area of this loop, our loop, minus the pumping loop. So A minus B will give us net indicated work of an engine. Now, of course, thermodynamically, we can talk about these areas without any problem. But if you have a diagram like this at hand, you can, of course, calculate this area and find out the work. But these engines operate at a very high speeds, at least 1,000, 1,500 revolutions a minute. Therefore, one cycle will be completed in a very small time duration. So for a second, for a minute, there will be lots and lots of PV diagrams generated. There are a lot of cycles. If it is a two-stroke cycle, if an engine operates, for example, 60 revolutions a second, then 60 cycles will be created. And if it is a four-stroke engine, if it rotates at 60 revolutions a cycle, the four-stroke cycle needs 2 complete revolutions to complete the cycle. Therefore, there will be 30 cycles in a second. Therefore, in practical sense, talking about this work per cycle doesn't make any sense, because we don't have any way of, in a practical engine, we don't have any way of getting this PV diagram, and at the same time, the cycle time is so short. Therefore, calculating of this, even though we get these diagrams done, there are so many cycles happening in the within a given time. Therefore, that is not a very good parameter to look at or express the capabilities of an engine. Therefore, what we do is we relate everything, all these things, to power, rather than going for work per cycle. When it comes to engine performance indication, we use power, that is work per second, rather than work per cycle, because cycle is something happening inside the engine. So we can convert this indicated work per cycle into indicated power, that is more sensible practical parameter, by considering the speed of the engine, as well as by knowing whether that engine is a two-stroke engine or the four-stroke engine. Now, if an engine operates, for the moment, let me use the term N as revolutions a second. Revolutions a second. If it is a two-stroke engine, in one revolution, how many revolutions are required to complete the cycle, the engine cycle? One revolution. If it is a four-stroke cycle, how many revolutions are required to complete the cycle? 2 cycles. You have to go through 2 cycles. Now, if it is two-stroke engine, if the indicated work is W, then if the engine operates at n revolutions a second, what is the indicated power? For 1 second, there are n revolutions. So one cycle produces W amount of work. So what is the indicated power? NW. NW, you have n number of, the engine rotates n revolutions per second. Indicated power is amount of work per second, and one cycle is W. There are n cycles per second, therefore Wn gives you amount of work that you produce in a second. So NW. And if it is a four-stroke engine, we'll have to divide that by 2. Of course, yes, because if the engine rotates n revolutions per second, that means per 1 second there will be n revolutions, and n divided by 2 cycles. Per 1 second there are n revolutions, but 2 revolutions per cycle, therefore n divided by 2 cycles. Therefore, the indicated power for any engine can be represented as Wn over Nr. Nr is an integer, where Nr equals 1 for two-stroke engines and 4 for four-stroke engines. So it's a direct conversion. So number of cycles per second, you multiply by work per cycle by number of cycles per second. Number of cycles per second directly related to the engine speed. So that is indicated work.